Good evening, my YouTube viewers. It is Crystal here. I'm just here because I want to give you a code review on a Kaggle data set about chest x-rays to see whether or not the individual has tuberculosis or not. And so basically this is a Kaggle data set. It's the tuberculosis TB chest x-ray database. And I was working on it all day long. And what I had originally wanted to do was I originally wanted to stack these pre-trained models, but it just wasn't possible for me to do it. It didn't work. And because it wasn't possible for me to do it, it didn't work. I just settled on the densenet convolutional neural network because I haven't used densenet before. So that's what we're going to do. We're going to do a code review on densenet. And it was a lot more difficult than it appears because you had to do set up the correct settings for the model, and then you have to set up the correct settings for the compiler. And so it was much more difficult to do than it looks. But I will go ahead and do the code review for you so you can see the code, and I will leave a link to the Jupyter notebook in the description box down below so you can look at the code and you can copy and paste it if you want to. So the title of this Jupyter notebook is TB densenet CNN, because what you're doing is you're checking to see if the x-rays have tuberculosis. And this is your problem statement. Classify an x-ray image as being normal or TB. So the first thing that we do after we have created the program, and I created the program in Kaggle's free online Jupyter notebook, and I don't get paid anything to promote it, by the way, is import the libraries. So what I've done is I've imported some of the libraries at the very beginning, and then I imported some of the libraries as I needed them, and then I imported all the Tensorflow libraries at one time when I started working on Tensorflow. So that's why you don't see all the libraries where it says import libraries, but I just imported the ones that I know I'm going to be using. So import NumPy as NP, which carries out numerical computations. Import pandas as PD, which carries out data processing, and it also creates data frames and series. And I would like to say that NumPy also creates NumPy arrays. Import OS to go into the operating system. Import matplotlib.pyplot to perform visualization of the data, and import Seaborn as SNS to also perform visualization of the data. So after we have imported the libraries that we will initially need, then what we will do is we will use OS to go into the operating system and get all the files. So these are all the files, and you can see it's a lot of them. So that's what we're going to do. We're just going to go through all of these files. And then after we have gone through all of the files, imported all of the files, or called up all of the files, then what we do is we import pathlib. And what pathlib does is pathlib establishes a directory. So data dir equals Kaggle input tuberculosis TB chest x-ray TB chest radiography database. And then data dir equals pathlib dot path data dir, and then you can see data dir, and there's your path. So we're going to define classes. We have two classes. Normal equals list, brackets data dir dot globe, and then it's normal slash asterisk, and TB equals list, brackets data dir dot globe, and then it says brackets tuberculosis slash asterisk. Then what we do is we print the length of normal, and then we print the length of TB. So you have 3,500 x-rays of normal and only 700 x-rays of TB. So now what we're going to do is we're going to print random images, because what I like to do is I like to build a random number generator and let the images come up at random. Because what some people do is they'll say, oh, well, print off the first image or print off 0 image or something like that. And I just thought, well, that's boring. I want to look at a different image every time I run the program. And believe me, I've had to run the program a lot to get it to work. So we import matplotlib.image as img, import pile.image as image. So then we set the figure up so it's going to have 2 columns, and the figure size is going to be 20 by 5, and then the subtitle is going to be category. And then what we do is we create a random normal equals np.random.randint, brackets -1 to the length of normal, and then we print rand normal. Then we print rand tb equals np.random randint -1 comma len tb, and then we print rand tb. So you can see that we printed out 2508 and 612. The 2508 was for the normal and the 612 was for TB. And then what we do is we make a normal image, img.imread normal brackets rand normal, and TB image equals img.imread brackets TB square brackets rand TB. And then so we set a title of normal and TB, and then we show normal and TB. So this is a diagram of normal and TB. So you can see that the normal X-ray isn't cloudy, whereas the X-ray with TB is cloudy. And so that's telling you if the X-ray is cloudy, that's telling you that the person possibly has TB. Which, this is a side note, but like my mom had to have an MRI scan or some kind of scan of some kind, and they told her that she has a spot on her lung and they were going to have to monitor it. So I'm not sure exactly what that spot on the lung is. It doesn't necessarily have to be cancer. It could be sarcoidosis, because that will give you growths and things like that. But that's just a side note aside from this code review, just to give you a little bit of information about me as the person who's giving you the code review. Now what we're going to do is we're going to define the data frame. So we're going to df images, and it's going to be a dictionary. So normal is the normal, and TB is TB, and then we define the labels as a data frame. So normal is 0 and TB is 1. So if when we do the predictions, if it's a 0, then it's normal, and if it's 1, then it's TB. Now what we're going to do is we're going to get a shape of a randomly selected image. So we're going to import cv2, img equals cv2.imread, string df images, then it's TB, and it's rand TB, so that's the randomly generated number for TB, and then you're going to get the shape of the img. So the shape is 512 by 512 by 3, so this is a three-dimensional matrix. Now what we're going to do is we're going to define our x and our y variables. So your x is your image and your y is your label. And so For label images in df images.item. For image in images, img equals cb2.iread bracket string image. Resize image img equals cb2.resize img, and you're going to resize it from 224 to 224. And then you're going to, X is going to be append resize images, and Y is going to be df labels label. So what you're doing really is you're converting the three-dimensional matrix to a two-dimensional matrix. And then so you've got 4,200 images and 4,200 labels, but 700 of them are going to be with tuberculosis and 3,500 are going to be normal. So that's telling you that you have a class imbalance. So now we're going to convert X and Y to NumPy arrays. X equals NP array X, Y equals NP array Y. And now what we're going to do is we're going to split our X and Y into training, validation, and testing sets. And we're going to use sklearn's train test split to do that. So we have one row of code to convert it to xtrain, xtestval, ytrain, ytestval. And then the second row of code is going to be xtest, xval, ytest, yval. And then we check the shapes of xtrain, xval, xtest, ytrain, yval, ytest. So you can see the shape of all of these matrices. So now we're getting into TensorFlow. So this is the point where I import all of the TensorFlow libraries that I'm going to need, and it's always important to go ahead and print the version of TensorFlow that you're working on. The reason for this is because TensorFlow has a lot of changes, and since TensorFlow has a lot of changes, it's good to know what version of TensorFlow you're on. Next thing we're going to do is we're going to normalize the data. So normalizer equals tf.keras.layers.rescaling, scale equals 1/255. And so that's your normalizer. And then the next thing we're going to do is we're going to define input shape to pre-trained models. So input shape equals 224 by 224 by 3, and input layer equals keras.input shape equals 224 by 224 by 3. But really, strictly speaking, you could have said shape equals input shape. Well, I didn't do that. You know, there's lots of things that you can do to change the code and make it more efficient. But since I had so much trouble getting it to run today, I'll just leave it as it is. But if you wanted to say shape equals input shape, you could do that. So we're going to set up the pre-trained models. We're not going to use VGG16, but I left it in there just in case you want to. We're not going to use MobileNet, but I left it in there just in case you want to. So we're going to use densenet. And so we've got input shape equals 224 by 224 by 3. Densenet equals densenet 169. Weights equals ImageNet. Input shape equals input shape. Include top equals false. For layer in densenet.layers, layer.trainable equals false. And so that's what we're using. We're using densenet. Now what we do is we define our model. So num label equals len brackets np unique y. So that's your number of your labels, or really the number of unique labels, because we'll only have 2 labels in this instance because it's a binary classification. And then what we do is we set up our model. Model equals keras.sequential brackets, square brackets, keras.input shape equals 224 by 224 by 3. So you could have just as easily said input shape. All of these places in the program where I say 224 by 224 by 3, you could just as easily say input shape, but you can see I've been working on it all day long trying to get it to work, so I just left it as it was. But that's something that you can do if you want to. And then what we do is the next line is normalizer, because we already defined the normalizer. And then the next line is, or the next layer is densenet, because we've already defined densenet. The next layer is keras.layers.flatten. The next layer is keras.layers.dense 256. Activation equals redo. And then the next layer is keras.layers.dropout 0.5. And the next layer is keras.layers.dense num label. And so num labels is actually going to be 2. So one thing that it had a comma there. I'm surprised that the comma didn't do anything, but it did work even though it had a comma there. So then we do model summary. So you can see this is a summary of the model. So you can see it's doing rescaling, and then dense 169. It flattens it, then dense again, and dropout, and then dense 1. So you can see all that. So I'm really surprised because we had this comma right here, and I'm surprised that it didn't crash with that comma, but it didn't crash. It worked anyway. And as I said, I'd been working on it all day long, and so I was tired, changing code, experimenting with code, seeing what I could find. And then so now what we're doing is we're compiling it. So model.compile brackets optimizer equals atom, loss equals tf.keras.losses, sparse categorical cross entropy from logics equal true, metrics equals ACC. And then now what we're going to do is we're going to train the model, and we're going to set the callbacks up for early stopping and MC. And I put it up for 10 epochs because I had to keep running it so many times to experiment with it to see if I could get it to work, that I finally just set it up for 10 epochs just to get it to work. But if you want to set it up for more, if you want to set it up for 20 epochs or even more epochs than that, you're certainly welcome to do that, because the training mechanism is set up for early stopping. So if it finishes training before you get to the end of the epochs, then it'll just stop anyway. So now what we do is we are predicting on X test. Ypred equals model.predict X test. Batch size equals 64. Verbose equals 1. Ypred bool equals np.arcmax. Ypred comma axis equals 1. Ypred bool. And then so you can see all the zeros and ones, and that's what it's looking for, zeros and ones. So now what we're going to do is we're going to use sklearn's accuracy score to get the accuracy. So you had an accuracy of 627. That's how many you got right. But let's look over here. Let's go back to X train, Y train. So it's 630 is X test. So it's 630 rows of data, or 630 examples on X test. And got 627 correct, so that means 3 were incorrect. So it was 99.5% accuracy. And then we evaluate it, and then you can see again it's 99.5% accuracy. And then we put it on the classification report, so you can see how it did on precision, recall, and F1 score. Now we put it on a confusion matrix. So on the number zeros, it got 1 incorrect, and on the number ones, it got 2 incorrect. And then now what we do is we put it on a data frame So what we're doing is we're comparing the actual values against the predicted values. And there were only 3 incorrect in all of that. So the next thing we do is we do some plotting. So you can see training and evaluation accuracy for every epoch. So you can see that. And the next one is loss for every epoch. So you can see that. So that pretty much concludes the code for this. And so what we'll do is I completed the code review, and I will leave a link to the Jupyter Notebook in the description box down below. So if you want to look at the Jupyter Notebook and if you want to copy and make those changes that I suggested that you make, or if you want to try a different pre-trained model to see which one works best, then you're more than welcome to do that. But after I've been working on it all day long, I think I'm just going to leave it as it is. So thank you so much to my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And thank you so much for watching my video. I look forward to making more code reviews for you in the future.